Now I notice we have quite a few people in the back row. Now I assume this is because you're not sure that this is going to be a good talk and you want to be able to head for the door. Okay. However, you'll get a much better view, and I'm going to be showing some props, and you'll be able to see it up close if you move from the back row up to the front row. So I strongly recommend that. Can we get some people to take advantage of that? Okay, and so let me get my props out. Okay, so this is one of my props. So I'm going to talk about solar cells, a subject that has interested me for a very long time. And everyone probably has seen solar panels. They're pretty commonplace in the world today, and especially in certain foreign countries. It seems like almost every barn is covered with solar panels in Germany. So it's become a rather big industry. In fact, the worldwide industry now is maybe close to $100 billion a year. So it's bigger than a lot of other branches of the electronics industry. And so we'll learn a little bit of it. You know what makes the subject interesting? There's science in it. There's economics, sociology, maybe even a little psychology in here. So it's quite interesting. So it involves society at many levels, not just at the scientific level. So, but on the scientific aspects, I'm going to mention a few things about the fundamentals of solar cells and how we achieved, recently a new record was achieved. It was achieved not by incremental improvements, but by actually introducing some new physics into it. So I'm going to tell you some things that are a bit counterintuitive. For example, I'm going to say that the p-n junction is merely optional. People sometimes think that the p-n junction is the critical thing in a solar cell. And it is sometimes needed, but it's really just optional. And then I'm going to talk about the voltage of solar cells. Now, it's much easier to talk about current because you see the current comes in, current comes out, and just have to be a good bookkeeper and you can figure out all about the current. But the voltage, you have to actually understand a little bit of physics. So I'm going to talk about the voltage. It is usually ignored. And then I'm going to talk about applying system mechanics to optics. And that's, you'll see that's helpful. People are often asking me, after you heard from Dave, is, great, our photonic crystals, surely they must be very useful for solar cells. So I used to say no, but now I'm saying maybe yes. And then I'll talk about the business aspects, the competing technologies, and the status of the industry, and those are the interesting parts. But before I get into it, as I promised, I have these props. So we have these new solar cells, and I have an example here. This is a film, a freestanding thin film of gallium arsenide, single crystal epi. As you can see, it's completely flexible, and it's not a little thing, it's a big thing. And Dave, you could have told this story is when I was at Belcourt, it took a week to create one of these that's only a square centimeter. And now it takes just a couple hours to create these. So this is the best semiconductor in the world, and it is epi, it is everything you'd want it to be. And it's also the material that broke the world record for solar cell efficiency. This is the same film when it's processed into cells. It's still very flexible, as you can see. And this is when you put them together to make an array as beginnings of a panel. So I asked the guys in the company, send me a dummy sample so I can show people what it looks like. And they sent me the sample with wires attached to it. And sure enough, it does produce electricity. Okay, so, come up and ask me to look at it. Well, I'll show you more of that toward the end of the talk. So this is just to whet your appetite a little bit. But we have to go through a bit of science at first. So please bear with me while I do that. One of the big questions to answer, first of all, is what is a solar cell? So I think that's a non-trivial question, so let me try to answer it. My answer is a solar cell is a container that takes in photons, and it contains the electrons and holes. So think of this container as maybe a piece of silicon. So that would be silicon. And light comes in, creates electrons and holes, and you're trying to build up kind of a high density of electrons and holes. And what you have is a selective contact. So electrical contacts to semiconductors are very, very hard. And so you're just lucky if you can make contact to electrons or holes. To ask for both is a bit much. So let's say you had one that was making contact toward holes, then the holes would go in that wire, and the electrons would go in this wire, and you would end up getting current out of the solar cell. Now, what could go wrong? Well, the electrons and holes, they could recombine. Famously, there could be dangling bonds in the semiconductor. And so you have to avoid that. Now, the most logical place to have dangling bonds is at the surface, where there's nothing to bond to. So universally, we always put a coating on our semiconductors of something with a larger band gap. And so the obvious thing on silicon is to put in a coating of silicon dioxide. And what this does, it prevents the electrons and holes from seeing the exterior bonds. And being that the silicon dioxide has a wide band gap, it holds both electrons and holes into the silicon. So a container makes a very nice container for the electrons and holes. And the way it benefits you is that with the electrons and holes not combining, you can build up a high density. Now, let me indicate why a high density is needed. If you think about the semiconductor, you know, in electrical engineering, we have a different way of thinking about the Fermi energy. For example, if you go to the physics department, you talk about the Fermi energy, and they say, yeah, Fermi energy. But an electrical engineer comes over and he talks about two Fermi energies, because there's a separate Fermi energy for the electrons and a separate one for the holes. At this point, you lose the physicists, because they never heard of having two Fermi levels occupying the same volume of space. But that's the essential thing in solar cells. And so if you're making, if one of the wires is contacting only electrons, it sees a higher voltage, and the one that contacts the hole sees a lower voltage. Now, the higher you build up the density of carriers, the closer the Fermi level comes to the band edges. And so there's a real premium to allow the electron's hole density to build up. And that's why you hate to have leakage paths, which would prevent the electrons and holes from building up. So now I've described what the solar cell is. It's a container for electrons and holes. Now notice at no point in my discussion did I describe a p-n junction. Well, some other things that could have come up. I just noticed, here's a reminder. How do electrons and holes know to go to this little tiny electrode? Well, they're driven by diffusion. And so if you go through the numbers, it requires just a few percent density gradient for the electrons to go all the way from this corner all the way down to the proper wire that they're supposed to go into. So, so it takes a gradient of density of maybe a 4% gradient in density to create enough diffusion to get the electrons to the proper wire. And likewise for the holes, they're driven to the other wire. Now you say, well, aren't you losing something because you're losing 4% of your density? But 4% of your density, there's a fancy name for that. We call that diffusion potential, and that works out to be less than 1 millivolt. So that's pretty negligible. So without loss of any generality, you don't need electric fields to drive the electrons and holes where they need to be. Just a tiny density gradient is enough to do it. Again, no p-n junction. So you say, well, the trick must have been in the contacts. So how do you make a selective contact? So here's an example. Let's say we have a kind of a heterojunction with a wider band gap, but the electrons can go freely through. So you're making contact to the electrons, but the holes, they get pushed back by that barrier. So this is a selective contact for electrons. Likewise, we could do the opposite, where the electrons get pushed back and the holes go straight through. And so this, at least in principle, is a way to make a selective contact. So it's not that hard to make a selective contact. And once again, I say you don't need to have a p-n junction. Now, so I have this model to describe how the solar cell works, and I call it the leaky bucket model. And imagine you have a pail, and the sunlight are these raindrops falling down. So the raindrops come in, they go into the pail, and you build up water. Water builds up in the pail, and you're going to take work out of this, because what you're going to do is you'll open a valve, and the water's going to flow out, and it's going to go down and turn the water wheel and have this output. And so the output would be the flow of water times the pressure of the water, because you need to have a little bit of pressure behind that faucet. And so that's your power, is the flow times the pressure, which is completely analogous to current times voltage. Okay, so it's completely analogous. Now, the analogy goes a little further. Suppose I have leakage of water out the sides. Okay. okay, and that we call that surface recombination. Or I can have a leakage at the bottom of the pail, and I'm going to call that bulk recombination. And the leakage, you hate to lose the water, but even worse, and very important in solar cells, is that the leakage means you can't build up as high a pressure head. And that turns out to be more serious than the leakage itself, is that it's going to prevent you from building up a high pressure head. So that's a pretty good model for solar cells. Now, there are only three things you need to know for a solar cell, and I'm going to teach them to you very quickly. One is the fill factor. I'll get into that next. The other one is obvious. You need to know about the current of the solar cell, and you need to know about the voltage. So let me answer what is the fill factor. And so let me illustrate it this way. Suppose I decide, maybe not too wise, to have a tremendous gush of water, open this valve wide open, so there's a tremendous gush of water. The tremendous gush of water means that you're not going to build up much of a pressure head. So you have it's like you have a lot of current, but you have no pressure behind it. So obviously that's unwise. And the water wheel will barely turn under those circumstances. On the other hand, you can go to the other extreme. Suppose you have the faucet almost completely shut and you have drip, drip, drip like this, and you build up a really big pressure head, but there's so little flow that the water wheel won't turn. So obviously that extreme is also unwise. So what you have to do is you have to optimize things. And this is just like in solar panels. What you do is you open the valve just the right amount, you get a decent flow of water, you get a decent pressure head, and you need to adjust. You can't go to one extreme or the other. You have to find the happy medium where you get the maximum power output. And that is what the fill factor is about, is finding that optimum. So here's an example of an IV curve of a solar cell. And in your imagination, you can imagine, oh, I'm going to get the highest voltage and the highest current at the same time. And you'd say, well, that's the big rectangle. But you can't get them both at the same time. You have to have a compromise. And so you compromise a little bit, and all you end up getting is the smaller rectangle. And so the ratio of these two rectangles is called the fill factor. And it's not that bad. I mean, ideally, it can be maybe up to 89%. So you can get 89% of what your fondest hopes were. But some people think of this and they say, well, it's really a pity. Too bad the IV curve is so crappy. But this is not a problem of just having a bad IV curve. This is really a problem in thermodynamics. This is something that you cannot avoid. And the way to think about it is that in statistical mechanics, if you want all of one thing, that's very low probability. Or if you want all of another thing, that is also very low probability. But if you're willing to make a compromise, then you have a high probability situation. High probability means high free energy. And so this is not just a problem of the IV curve. This is really fundamental thermodynamics. And what's really going on here is you have to give up a little voltage in order to get the electrons and holes, give them a reason to go into the wires. They're happy in the semiconductor. Why should they go into the wires? And so this is pretty fundamental. You're balancing off probabilities and trying to go to the highest free energy state. So that's what the fill factor is about. It's achieving this happy medium that occurs here. Okay, so let's say you're okay with that. Let's go on to the current. So I promised we'd go quickly. So that was fill factor. Now we go to the current. And with current, the problem is just to absorb the light. And you want to absorb the light in as thin a layer of material as possible. And so you say, well, let me use a direct band gap instead of an indirect band gap. And because I'll end up using less material. Now let's say we're talking, as I am about here, I'm talking about gallium arsenide. You say, oh my God, it's a direct band gap, but it's a more expensive material. But wait a minute, it absorbs hundreds of times more light. And it's 10 times more expensive than silicon, but I can use hundreds of times less material. So if you ask me, I will answer that the more expensive material is actually cheaper, because it's a direct band gap, you need much less material. And so that's one aspect of absorbing the light, is you want to have a strong absorber, because then you won't need very much of it. And by the way, these films are about 1 micron thick. Okay, so fine, maybe we'll use a direct band gap. Now what about absorbing the light? Well, here a problem comes up. And that is the light comes in, and most semiconductors have a high refractive index, then you refract toward normal, and then it goes right back out again. Hey, don't complain, at least you got a single pass. But what if you change something? What if one of the surfaces was rough? Here I show both surfaces as rough, but only one needs to be rough. And so when the light comes in, it refracts at some odd angle and does not immediately find the escape cone. And then it scatters off at some other odd angle because the surface is rough. And before you know it, it has no memory of the original angle it went in, and it's at a random angle, and now it's at a random angle, and it's trying to find this very narrow escape cone. Now, the refractive index of most semiconductors is 3.5. Very different from glass, which is 1.5. 3 point, that's a huge refractive index. And so this escape cone is extremely narrow, maybe 14 degrees. So it bounces around an awful lot before it ever escapes. In fact, you can go through some little reasoning, and you can prove to yourself that it bounces around and increases its internal path length by 4 times refractive index squared. Now, index 3.5 squared is 12 times 4 is 50. So the internal path length in the silicon or in the semiconductor is increased by 50 times. So that's huge. I mean, means you're using 50 times less material. So that's very, very enormous and very surprising. Now, up until about 10 or 15 years ago, they made solar cells this way. And starting about 2000, they started making the solar cells this way. And it's kind of shocking that it took that long for them to get to that. Now, in this regard, it was around the same time they started being more sophisticated with light emitting diodes, because what is a solar cell? It takes in light, produces electricity. The light emitting diode takes in electricity, puts out light. So they should be similar. So I just described to you the situation in the solar cell. You need to break the plane parallel symmetry. Light emitting diode, it's actually the same thing. It's a reciprocal device. It should be the same. If you make or buy an ordinary light emitting diode, like the ones made before 2000, let's say, yeah, 2% of light would escape through the escape cone. 98% of the light would just bounce around and eventually get lost because it can't escape. So what they've started doing, and all LEDs do this now, is you break the plane parallel symmetry of the semiconductor. You put in some shape to it, and yes, it bounces around. It still has trouble finding the escape cone, but it has multiple attempts. And finally, after numerous tries, it escapes. And in this way, if you break the plane parallel symmetry, all the light eventually escapes. And now we have LEDs with efficiency well over 50%, where it used to be LED efficiency was 2%, you patted yourself on the back. Okay, so that it's a world of difference, and all you've done is something geometrical to change the plane parallel symmetry. Now, in this respect, you've learned everything you needed to learn when you were in kindergarten, because in kindergarten you are taught about different shapes. Maybe that's an advanced kindergarten, I don't know. But let's say you're taught about the sphere. But there's one thing advanced, is the name we give it. So when I was in graduate school, I took a course in statistical mechanics, and I was taught the word ergodic and the word non-ergodic. And I finished the course, and phew, I'll probably never have to use that word again. Okay, and here it comes up. So I'll show you, and it's kindergarten stuff. So let's say I have a shape that you're familiar with, like a sphere. The light ray comes in, it refracts, and refracts right back out again. It does not explore all the internal possible angles because it can't. When it comes in, and it can always escape. Same with a rectangle, okay? And same with a parallelogram. So in these cases, the light rays do not explore all the possible angles. So all the possible angles is the phase space, okay? So those are the non-ergodic shapes. Now, conversely, if you have light inside, that light could be trapped forever, could bounce around forever inside the sphere. So it's kind of an issue. Now, let's compare that to the ergodic shapes. So now we're in kindergarten, and we're separating the shapes into categories. So some are ergodic, some are non-ergodic. So the ellipse can be, you can actually come in, and the angles can be rather funny. Before you know it, you're filling all the possible internal angles. Same with the trapezoid. Or conversely, if there's an internal light source, all of the internal light eventually escapes. And so here we have a categorization of shapes into ergodic means the average over all possible angles is the same as the average over time. So you average over time, you eventually explore all possible angles. That's ergodic. And on the other hand, we have examples that are non-ergodic, and it's just the geometrical shapes. And so we used to make LEDs and solar cells like this, and now we make them in a way where we respect this, this need to have an ergodic shape. So I mean, they've got pyramid-shaped LEDs, and they all sorts of weird shapes. Okay, so that's the light trapping. It's a pretty good thing. Now, people often ask me, yes, this 4n squared factor, but where does it come from? So if you look at the density of optical modes and you do a density of states, there is a refractive index squared that appears in it. So obviously a high index, there are more wave vectors that are possible. So I pick up a factor of n squared. Then I pick up a factor 2 from double pass, because if you're just reasonably alert, you'll definitely do double pass to get the most absorption. And then when you're inside the solar cell, you'll be going at an angle, because now all the angles are acceptable, and you have to average over angles. So you have to average over cosine theta. So compared to going vertically, which is what we used to do, versus going at an angle, you can figure out that cosine theta averages to 2. 1 over cosine theta averages to 2. So the net benefit then is 4 times 2 times 2 times n squared. So that's 4n squared. That is the benefit. And that's has a huge effect on solar cells, LEDs, and is important in optoelectronics. Now, so what is the benefit? Well, you can use 50 times less material. Hey, if you're worried about the cost of the material, 50 times less. That's not bad. Okay, and then if you have a thinner cell, maybe the current doesn't have to go as far. There could be less series resistance. But by far, the most important point is that you have taken the electrons and holes produced by sunlight, and now you have crammed them into a thinner solar cell. So they build up to a higher density. Now, in chemistry, you are taught if you have a higher density resource, the free energy goes up. And in fact, the free energy goes up to the, as the ratio, the natural log of the concentration ratio. So effectively, you have increased the concentration of electrons and holes by whatever amount that you made the solar cell thinner, because you can get away with a thinner solar cell. And the free energy boost is kT log of that concentration ratio, which is natural log of 50, which is about 4, and 4 kT is about 1/10 of a volt. So now you're gaining current, but you're also gaining voltage. And the voltage, well, 1/10 of a volt may not seem like much, but you know all those silicon solar panels that you see out there in the fields? They're typically working at around 1/2 a volt. So if you add 1/10 of a volt, it's pretty significant. But here is a problem in the English language. They say, great, you're going to take advantage of total internal reflection to trap the light. How is that going to be compatible with the anti-reflection coating that all solar cells need? So you get worried. Total internal reflection, anti-reflection, they're contradictory. But actually, they're not contradictory. Every solar cell should have both. If you're in the escape cone, you have to be concerned with the anti-reflection coating. But the anti-reflection coating has no effect whatsoever on the total internal reflection, which is influenced only by the refractive index ratio between the inside and the outside world. So it's just a problem of the English language there. Okay, now here is the question that people ask me all the time is, when I wrote this paper a long time ago, I said that you can pick up this 4n squared factor, and I also said in the paper is that you can't do better than a random surface. And the reason is the random surface was already giving you 4n squared. That is the amount decreed by statistical mechanics, and therefore you can't do better than statistical mechanics, therefore you can't do better than a randomly rough surface. However, over the years, this idea has received considerable criticism. Many people have stepped forward and said, I can do better than random. Random is just naive, and I can do better than random. Now, I got into a lot of trouble with this. I did this first when I worked at Exxon with Professor Bernholtz, and we were there together, and somebody at the company came up and said, I can do better. I have this special thing with the gratings and all this, and I can do better. And I was kind of fuming. I was sitting in the audience listening. I said, no, that's wrong. You can't do any better. And so on. And I said, well, how can I reply to this person? And so I replied with the worst possible insult you can ever give anyone in an energy company. And that is to say, if your scheme works, it's a perpetual motion machine, right? Because you'll be defying the second law of thermodynamics. And they said, oh, no, we're not making a perpetual motion machine. No. So the defense, so basically you couldn't do it. But over the years, people have thought, well, what about a photonic? Yeah, maybe you can do better with a photonic crystal. And indeed, I covered this in my original photonic crystal paper, and I said you couldn't do better. But I think there is a circumstance in which you do need a photonic crystal, and random patterning won't do the job. And let me show you the circumstance in which that is. Suppose you had a gallium arsenide solar cell, and you wanted to, and it's direct band gap, you want to really absorb all the light. You could make it 3 microns thick. Then you'd be 100% sure that you're absorbing every last solar photon available. Now, if you do the texturing, then you pick up 4n squared factor. Now it's 60 nanometers thick. Now, nobody today talks about making solar cells 60 nanometers thick. But in the future, they will, because we keep making them thinner and thinner. Why shouldn't we go all the way to 60 nanometers? Now, if you're 60 nanometers thick, you're actually thinner than the wavelength of light. Now, what is the meaning of random roughness if you're thinner than the wavelength of light? I don't think the term random roughness means anything if you're thinner than an optical wavelength. And so at that point, I think you have to have some kind of deterministic pattern. And so that becomes a situation, and most likely that deterministic pattern will satisfy periodic boundary conditions and will be indeed a two-dimensional photonic crystal. So I assigned the problem to a student, and the problem was find the texture on a thin film, just thin film optics, but should have some texture to it. Find the texture that ends up absorbing the greatest amount of light. Okay, and let's see, this might be a movie. Let me get out of pen mode and see if a movie, yes, there is a movie here. Okay, so we have some sophisticated math. I don't want to get into the optimization mathematics, but her task was to investigate different surface textures with the idea of getting the most absorption. Now, gallium arsenide, although it has a direct band gap near the band edge, it's not such a strong absorber. And so she was covering this region between 350 and 400 terahertz. By the way, I don't like wavelength, I prefer frequency, so this is in the near infrared. And the gallium arsenide is not that absorbing, and I need to optimize it. And she was looking for this 4n squared factor and see if she could get close to it. And so she did this optimization. It's an iterative optimization. Let me show you the movie. And basically on the left side, look, she's trying to get good enhancement over the whole frequency band. Okay, so let's see what happens. So now she's iterating, and this algorithm is constantly trying to improve the worst performing frequency, and here's how it ends. So it ends with about a factor 20 enhancement over what a plane parallel thin film would have been. So it's actually very close to the theoretical limit. And she has interesting things like symmetry breaking. So when you're doing optimization problems, you often get spontaneous symmetry breaking. But I don't want to dwell on this, but there's a whole science like this, is how do you organize a thin film so it absorbs the maximum amount of light? And plane parallel is not the correct answer, because you can absorb way more light than plane parallel. So this is one answer. There are many other answers. Let's see. What you do find when you do this math, you tend to use periodic boundary conditions, so it automatically turns into a two-dimensional photonic crystal. But where you get the best performance is in the band structure. You have stuff down here, normal band structure, but the place where the solar cell wants to be is in the higher bands, where you have many bands, and we call it the spaghetti region of the band structure. You have many bands going all over the place. That turns out to be the best place to put the weakly absorbing parts of the solar spectrum. And she ends up with the final performance. It ends up with weird shapes like this. So the whole talk in itself is to try to understand this part, but let me say that that's all I want to talk about with regard to current, is that we can trap the light internally by various means. We can get greatly increased current, and this is in common use in everyday solar panels, is to do this. But mostly it's done with random textures. By the way, when I first published this paper, nobody understood it. I don't think it was that complicated a paper, but when I would explain to them they thought, oh, you're texturing the surface to make a better anti-reflection coating. And it's because sometimes people used to do that. And no, it has nothing to do with that. It's so the light would get trapped internally. It has nothing to do with the anti-reflection coating. And so I experienced a lot of resistance to this idea. And however, the aficionados figured it out pretty quickly, and they published a couple of follow-up papers, but the industry really did not adopt this until about the year 2000, which amazes me that it took them that long. But that's sometimes a simple idea. It's very hard to get it across. Okay, that's all I want to say about current. By the way, people are free to interrupt at any time. And I'm going to pause now. I'm switching from current to voltage. Does anyone have any questions, interruptions? Go ahead.
Back to the polarization. Is that talking about the polarization of the light coming in?
I didn't notice. Oh, yeah, no. When she optimizes, since sunlight is unpolarized, she has to optimize for both polarizations. So that's this stuff here. And so she optimizes for both. And for both of them, she got a good 33 times enhancement. Now, given that this film was already, it had already got you very close to 100%. So in this case, you didn't expect much more than 33 times enhancement. So it's pretty good. And when you do it, if you're going to optimize, you have to optimize for both incoming polarizations. Okay, let me jump ahead to voltage, because this is the final thing we have. Now, the voltage to me is the most fascinating. So you'll see in a minute why it's the most fascinating. So I'm going to talk about the open circuit voltage. The reason is, if I give up a few kT, this is the actual difference between the operating point voltage and the open circuit voltage. You give up a few kT, and you drop down from the open circuit point to the operating point. So if you can get a tremendous open circuit voltage, you're done. Then you'll get a tremendous voltage. Okay? Now, voltage is very hard to explain. However, if you accept one thing that you learned in freshman chemistry, is you learn about the Boltzmann factor. And the Boltzmann factor ended up looking like this. It was an exponential. And on the right-hand side, we had a probability ratio. And I want the probability ratio to be the probability of being in the excited state with the sun shining. But even at night, there's still some probability of being in the excited state just thermally. And that's the ratio of probabilities that I want to associate with a Boltzmann factor. And if I believe they still teach Boltzmann factors in freshman chemistry. If you accept that, I can go a little further. I can take the natural log of both sides. And if I take the natural log of the left side, I end up with the numerator, which is the free energy, which I'll identify with voltage. And on the right side, I'll have the logarithm of the probability ratio. So if I knew this probability ratio, then I could determine the expected voltage. Okay? So that's pretty straightforward. Now, notice the formula is fine. However, if you're dealing with a semiconductor, this formula is fine for quantum dots and molecules. If you're dealing with a semiconductor, there's actually a 2 in here. And when I was at Exxon, we had the Nobel laureate Bob Schrieffer was a consultant. And he'd come in from time to time. They must have been paying him, like, in today's dollars would be $10,000 a day. You know how it is when you're a Nobel laureate. But he was a smart guy, but he had to suffer for his money. They had management review meetings. And being that he was a high-paid consultant, they made him listen to the management review talks. Yeah. And I was a manager myself also at the time. And so I was sitting in the back with him. We're both bored very, very stiff. And I showed him this without warning. I showed him this, and I said, sometimes there's a 2, and sometimes there's not a 2. And it took him about 15 seconds to figure this out. And he said, well, in this case, you have the phase space of both the electrons and holes. You have twice the phase space. And so the probability comes in with a square. And so you get a 2 out front. I was flabbergasted. Well, this is the correct explanation. But this was not his field. And he figured this out in about 15 seconds. Okay, without any preparation or any warning. And what it shows is that your average Nobel laureate in theoretical physics is smarter than your average person. I think that's what it shows. But usually I give this talk, I don't tell the story because it's too far off topic, but it's kind of fun to manage. So yeah, see, Schrieffer explained to me why sometimes it's 2, because the phase space is twice as big. Okay. However, let's go to without the 2. Okay. Now, so the question is, how do you know what is the population ratio? It says, well, if it's in the excited state, you emit light. So I don't have to know the population ratio. I just have to know how much light it emits. So if you're excited in the under the sun, yeah, of course you're going to emit some luminescence. However, even in pitch darkness, you'll emit some light because there's a little bit of blackbody radiation you'll emit even at room temperature. So here's where Shockley comes in, and this is a very famous paper from 1961. He says, well, in the numerator, that's the amount of light. If I want to know the population, it's proportional to the amount of light that's emitted. However, even in equilibrium in the dark, I'll emit a small amount, and that would be the blackbody radiation. So Shockley tells us exactly how to do this. Is you put in the, well, he takes one more step. He says, well, I don't happen to know the amount of light output from the solar cell, but there's an easy way to know. Is that suppose you operate the solar cell at open circuit, so the electrons and holes have no place to go. If they have no place to go, the only place they can go is to luminesce and go back toward the sun. And so he said that the ideal solar cell at open circuit, all it can do is the external luminescent emission. For every photon of sunlight that comes in, that has to be emitted as a luminescent emission. So he says in the numerator, I'll just put the incoming sunlight, because that's the amount of luminescent emission I expect. In the denominator, I have something I can calculate, which is the blackbody emission in the dark, and now I can calculate the open circuit voltage, because I know the incoming sunlight, I know the blackbody emission, and that ratio, KT log of that ratio, gives you the open circuit voltage. So Shockley figured that out, and he was, of course, a very brilliant person. However, there is an easier way to do this that I prefer. And this is a recognition that photons have entropy. Now, I could ask you, what is the entropy of sunlight? I imagine that nobody has ever taught you the entropy of sunlight, so it's my obligation to do that now. Now you say, well, do photons really have entropy? Well, if you ask an astrophysicist, the person who studies stars, is yes, definitely the radiation does have some entropy in it. So, well, what about sunlight? How much entropy does that have? So I will ask a little differently. How much free energy is there in the sunlight? Now, one of the things that you're taught in physics is U minus Ts. The free energy is U minus Ts. And U is the energy, so it's obviously the photon energy. But S is the entropy. What is the entropy we can associate with photons? Well, if you take system mechanics, the entropy is the logarithm of the number of different ways we can arrange that object. And so for the sunlight, it's the number of different ways I can arrange the sunlight. It doesn't help me, though. It's a little vague. So this viewpoint, though, is I'm going to tell you how many ways you can arrange sunlight, and you'll get the entropy, and you'll end up getting the free energy, which is the voltage. Now, this is expressed on this slide in a form that I first read from a paper written by a graduate student at Berkeley. He was a graduate student 50 years ago. And he was not in electrical engineering. He was in chemistry. And he was actually, his thesis advisor was someone very famous in chemistry, Melvin Calvin, who was very busy trying to understand photosynthesis. And he eventually got the advisor got the Nobel Prize for explaining photosynthesis. Along the way, he had to figure out what free energy you might get. That was in the 1960s. It was after Shockley wrote his paper, and they were very inspired by Shockley's paper, and they realized that photosynthesis follows exactly the same way, almost exactly the same as a solar cell. And so he figured out the free energy. And this is the way he did it. He says, well, you start with a photon, let's say it starts at the band edge, and then I'm going to have to subtract off a bunch of entropy terms. So I'm going to go through these entropy terms one by one. And the dominant one is the first one. And the first one is the recognition of the following fact, that if we step out in the parking lot, we can see the sun in the sky. It's a disk about half a degree wide in the sky. And when you make a solar panel, though, you don't take advantage of the knowledge of exactly that angle that the sun is in the sky, because you have sunlight from all the different angles from the rest of the sky. You hesitate to throw that away. And because you hesitate to throw it away, you throw away Instead, you throw away the information. You want all the light from all the sky, but you throw away the information on exactly the angle that the sun was in the sky. Now, when you throw away information, that leads to entropy. That's the number of combinations. So I ask, how many different places in the sky can I put the sun? It's half a degree, which is about 1/100th of a radian. And then I square it to get the solid angle, so it's 1/10,000th. Then I put in a pi. There are actually 30,000 places in the sky where I could put the sun. Okay? And that means the number of combinations was 30,000. Natural log of 30,000 is about 12, and then 12 kT is about 3/10 of a volt, and that is the biggest entropy term, and that is the biggest drop in voltage. You never get the band gap. You immediately give up roughly 3/10 of a volt due to the solid angle subtended by the sky. Now, I once explained this to one of my colleagues, and says, wait a minute, this has nothing to do with astrophysics. We're talking about solid-state physics here. Why does solid-state physics care about the solid angle subtended by the sun? We're not doing astrophysics. And the answer to that is, well, yes, but you still have to know the nature of the resource. And so you do need to know the solid angle subtended by the sun. And that entropy associated with throwing that information away is the biggest part of the entropy. So you lose 3/10 of a volt here. Now, you lose another 1/10 of a volt. Remember I told you about the 4n² factor? Well, that angle in the sky is even sharper when you refract into a semiconductor material. The light rays refract, and they could refract like this. And so the angle is even smaller once you get inside the semiconductor. If you take no advantage of that, and you're oblivious to it, you will lose this 4n² factor, and you will lose that concentration. And I already said natural log of 4n², you lose another 1/10 of a volt if you build a naive solar panel. Now, you need another 1/10 of a volt to give the electrons and holes a reason to go into the wire. Okay, so that has to do with the fill factor, and we discussed that. Now, this loss here vexes me very much. It's unnecessary, and was recognized, at least indirectly, in Shockley's original paper, is that he said the best solar cell, for every photon of sunlight coming in, it gives you a luminescent photon. Well, most solar cells don't luminesce that well. In fact, there are some solar cells that luminesce horribly badly. And I was giving a talk on this in Washington, and I recommended very highly to look at the luminescence. And question period. So it says, well, my solar cell doesn't luminesce at all. And I thought of something unkind to say, like I was going to say, maybe I even said this, is that maybe you should pick a different material, because they have amorphous silicon solar cells. The luminescence efficiency is 10⁻⁵. Why bother? That's another 3/10 of a volt that you lose. That's pretty sad. There's a few minor corrections at the end. I'll skip that. So what does it tell you is you've got to be very careful with the voltage. If you start with band gap of silicon 1.1 volts, and you subtract all those entropy terms on the previous slide, they add up to 0.8 of a volt, and you could end up with a crummy 0.3 of a volt at the operating point. And that's pretty sad. Considering that you're starting from 2-volt photons. That's really quite sad. So what it says is you cannot mess around with the voltage. You can't just sweep it under the rug. You've got to do a good job with the voltage. Okay, and also tells you avoid narrow band gap solar cells. There's a lot of photons in the infrared, but they don't have much free energy. There's also a lot of entropy in the infrared. So don't vex yourself. Don't worry about capturing those infrared photons. There's energy, but there's not much free energy out there. Because whatever the band gap is, you subtract a fixed amount. So if you start with a small band gap, before you know it, you're getting nothing. Okay, so now let me talk about the new voltage, or new record efficiency. So I plot here the efficiency versus year, the record efficiency for a single-junction flat-plate solar cell. And for almost 20 years, it was stuck at 25.1%. And then in a couple of years, and suddenly, I say I need to revise this because it hasn't gone up either. It continues like this now. There was a step function in the efficiency. And it was not a trivial amount because it went to almost 29%. So this is not like shaving 1 second off a record. This is like a giant leap from 25 to almost 29% efficiency. Now, it was entirely due to a leap in voltage. So the previous record gallium arsenide cell was around 1.03, and the new record was 1.12. And that was rather surprising. In fact, at the company, I'm the co-founder of this company. At the company, they started getting big voltages, and I said, whoops, something interesting is happening. I've never seen a voltage like that. And then I told them how to go further, and this is the record voltage. So it's almost 1/10 of a volt, so it's a huge amount. That's responsible for the record. Now, what it tells you is the following. The world had been stuck for 20 years at 25% efficiency. In order to, but the Shockley limit is about 33.5%. So to get to the new regime, we had to have some new physics. And the new physics had to do with the voltage. So let me show you what is the new physics. This is the way you see a solar cell described in textbooks. The sunlight comes in, and electrons and holes are produced, and they get collected. And that's the picture that people have of solar cells. However, to have high efficiency, the picture has to change. Let me show you the picture today. The picture is the sunlight comes in, it produces an electron hole pair, that instantly recombines back into a photon. The photon bounces around, gets reabsorbed, produces another electron hole pair, which recombines, produces a photon again. Absorbed, re-emits. Absorb, re-emits, finally does not re-emit, instead gets collected, okay? Or, of equal importance, is that sometimes the photon just escapes. And you might think that's bad, it's actually good for occasionally a photon to escape from the front surface. Okay, so this is a very different picture than what you have in textbooks. In this picture, when the sunlight comes in, you might have one sun falling on the cell, but if that cell is a high-performance cell, you will trap 30, 40, or 50 suns of infrared luminescence inside. And that's a requirement for breaking records and for getting close to the Shockley limit. And so it's a very different picture. And a lot of that luminescence is trapped inside and is constantly being recirculated. And it's a necessity for achieving the high efficiency. And indeed, this is what Shockley told us. Maybe not in so many words, but this is what he meant, is that you'll get your ideal voltage, but if it is accompanied by perfect luminescence, to say for every solar photon, you end up emitting light. And if you fail to achieve 100% external luminescence, you will not get the ideal voltage. And if you achieve 1% luminescence, well, you'll lose natural log of 100 times kT. You lose 5 kT. So it's quite significant. And also, since it's balancing incoming sunlight, it doesn't matter what's going on internally. You have to have some external fluorescence. And that's why I said you need some of the light escaping externally. It's very surprising. And this tells us how to get a high voltage, is to get a good external luminescence. But it's hard. The reason it's hard is the escape cone is so narrow. Indeed, because you're constantly recycling, you might need an internal efficiency of 99% just to get the 50% out, because it's going to be reabsorbed internally many times before it gets out. So this is really hard to do. Wow. 99%, and it just gives you 50% external efficiency. So it's very hard to do that. However, the 3-5 materials are an amazing gift of nature because they are the most efficient. They will actually give you well over 99% luminescence efficiency at room temperature. So they're quite remarkable. Now what about the reflectivity? Since you're bouncing around internally, you better have a good rear reflector. The ones I'm showing you, you can see, this used to be a company secret, there's copper on the back. And you get quite a good reflectivity. How good does it have to be? Well, 90% is not good enough. In fact, if you look at the efficiency as a function of reflectivity, your best region is above 95%. So that's where your rate of improvement is the greatest. So 90% is not really enough. And same with the internal luminescence efficiency. Again, 90 is not enough. You want close to 99 if you can. So that's part of the secret. And so this ends up then in this record. This is the current standing world record for solar cell efficiency. By the way, nobody measures their own efficiencies. You always send it to an official government lab, and somebody else measures it, and they verify what you had. Okay, and so that's where it is. It has the high voltage associated with it. Let's see, there's the voltage. I can tell you we did present this at a photovoltaic conference, and the presenter was one of the young scientists working at the company. And he presents this, and everybody's stunned because it's a new record. And but they're particularly stunned at the voltage. They don't believe the voltage. They've never seen a gallium arsenide solar cell with such a high voltage. First question, was this really gallium arsenide? Answer, yes. Second question, was it very thin, so you had you got quantum confinement and the band gap got bigger? As no, it's micron thick. Okay, so that was the attitude, is that this is a surprisingly high voltage. And it comes from this mechanism. In order to get the high voltage, you need to have an internal luminescent photon gas. It's an absolute requirement to getting high voltage. And that photon gas has to be way more dense than the incident sunlight. Could be, the density increase could be as much as 4n squared. And so this becomes a requirement. And also you have to be able to get light out. That also becomes a requirement. That's decreed by Shockley. But it's hard because 90% is not enough. So to summarize this part, if you have a solar cell of 25% efficiency, stop worrying about electron hole transport. Don't even bother with that in your solar cell model. If you want to go above 25%, it's all about photon management. It's all about assisting the internal photons to escape and to emit it externally. In fact, there's a mantra that came out of this. And the mantra is, a good solar cell has to be a good LED, and a great solar cell has to be a great LED. Okay? And so the way to make the highest voltage is to get the best external LED efficiency. I can tell you a little bit about the history of this. They started getting these higher voltages, and they had a, and I told them that you keep improving that rear mirror. So they had a 96% reflectivity mirror, and they broke the world record. And then 6 months later, they, with the same material, the mirror was improved to 97% reflectivity, broke their own record. And then they improved the mirror to 98% reflectivity, and that's the current world record, and they broke their own record again. So nothing was changed about the material. It was all about the photon management that made that possible. However, it's a bit counterintuitive, because it says that the best solar cell is the one that gives back infrared light, gives back photons. And that is extremely counterintuitive. Why should a solar cell, which is designed to take in photons, why should it give anything back? It's very, very puzzling. And I had a devil of a time trying to explain this to people. And so I'm going to try to see if I can explain this paradox. This is the key paradox. This is why we broke the world record. So how do we explain why you should give back? Well, here's one possible explanation, is that the recycled photons are not lost. They recreate the electron hole pairs. The effective electron hole lifetime increases. If they hang around more, you can build up higher density. I already said density, log of density is voltage. So this is one possible explanation to think about this. And this is one that some people like. But this is a very incomplete explanation. For example, you don't have to recycle the photons. You can just texture the film. You'll still get the voltage increase. So now I have a bunch of other explanations. And so these are a bunch of... the trouble, why do I have 5 explanations? If I had one good one that would satisfy you, I could stop there. So I'm going to skip all these lame explanations, and I'll go to this one. To me, it's tautological. When you measure the luminescence from a solar cell, you're effectively measuring the internal voltage. Now, I can show you this, that there's a formula you can derive from statistical mechanics. You know, the luminescence is proportional to the NP product. You can generalize this. The luminescence is proportional to this factor. So the more luminescence I have, the more voltage I have. And so I say it's tautological. The luminescence is voltage. It's a voltmeter. And indeed, in manufacturing plants, they will sometimes use the luminescence as a quality control metric. They'll put out an array of solar panels, and they'll take an infrared snapshot. And let's say, and they'll luminesce. Even if they're silicon, by the way, they will luminesce some. And then they'll see one that's dark and not luminescing well. You don't chip that one. That one's a bad panel. Okay, so they're using it for quality control. A good solar cell should luminesce well in the infrared. And this viewpoint is tautological. Well, why do you need good luminescence? Because you want good voltage. And so that is my preferred explanation, although other people might prefer different things. And it's all really about this formula that was implied, not written, but implied by Shockley. In fact, the first paper I saw that actually had this exact formula was that paper by the graduate student Ross. It says, whatever voltage you think you ought to get, you better subtract off your luminescence efficiency. But I still get a lot of complaints. My solar cell doesn't luminesce, and yeah, well, that's a pity. Maybe bad solar cell. Then they say, well, I have to separate the electron hole as quickly as possible. Therefore, they don't have a chance to luminesce. All a bunch of lame things. You do need luminescence. Okay, so what about tandem solar cells? Of course, in the future, we're all going to have tandem solar cells. Because why stop at 28.8% efficiency? So in this same film, at Alta Devices, they simply grew another couple of layers of indium gallium phosphide. They were already using that compound as a window on the solar cell anyway, so there's no added complexity to add a second junction. They added a second junction with indium gallium phosphide, and they made a dual junction. So it looks just like this. You can't tell the difference, except when you send it to be tested by NREL, now there's a new record. So they got up to 30.8% efficiency. They got into the threes and then they stopped. NREL kept going. NREL went over, using the same approach, they have gone over 31% efficiency. And this approach is capable of maybe 34% efficiency. So from now on, it's all about multi-junctions. This is dual junction. The beauty of this is all lattice matched, no added capital equipment. It spends another few seconds in the growth reactor. So over 31%. The CEO said, from now on, unless your efficiency starts with a 3, don't talk to me, okay? And so I wish this message would get across because some people are still bragging about 10% efficiency. Now, how do we make this cheap? So they say, great, it's wonderful, but this is gallium arsenide. It's such an expensive material. Well, I already told you the clue is you don't use much. Now, here's how you arrange that. And this is a process I developed when I was working under Dave Asmus, and that is to take advantage of something that is kind of amazing, and that is etch selectivity. And if you go to the Handbook of Chemistry and Physics and look up the inorganic compounds, now nobody does this because you have the web, but in the old days we actually had the volume. It was a very thick volume. And then you look up the inorganic compounds, and it has a list of all of the known inorganic compounds. And then it tells you the color, and it tells you the melting point. And the last column in the Handbook of Chemistry and Physics was rather cryptic. It was I or S. And the old timers, I hope, remember that. I or S. Well, what does that mean? It was soluble or insoluble. Why is it binary? So there's an interesting question. Why is it binary? Why is it either, and then rarely it will say SLS, slightly soluble. That was rare. Mostly it was either soluble or insoluble. Now it turns out with gallium arsenide, it's the same story. Acids will attack the aluminum-rich alloys and not attack the gallium-rich alloys. So if you make an epitaxial structure with a very thin layer of aluminum arsenide and you put it in acid, it's not going to attack the gallium-rich alloys, and so the acid will come underneath and will float the film off, and it'll pop off, the film will pop off, and the substrate will be ready to be reused again. So the reason why it's low cost is you're not wasting all that money on the substrate. You're going to reuse the substrate over and over again, and you're only using the amount of gallium arsenide you need, which could someday be as little as 100 nanometers worth or 60 nanometers worth. So it's an insignificant amount of gallium arsenide that you end up using. And it's due to the direct band gap and the light trapping together. You'll end up using very, very little. Now, so over the years, I started experimenting on this 30 years ago. It turned out even before me, a Japanese group had been doing this. They published a paper about 10 years before me. But it had a lot of problems associated with it. But I can announce now the problems are all solved. This is actually some old work from Netherlands. This is 2-inch. So what I'm showing you here on the diagonal, this is 6-inch. This came out of a 6-inch gallium arsenide wafer. And what they do is they put the wafer, it's not done the way the Dutch showed it here. It's more like this. You have a cassette with 1,000 wafers. You dunk it into hydrofluoric acid. You come back in 2 hours. You take it out and rinse it, and it looks like nothing has changed. But actually, the entire underneath of the film has been undercut. And then they come along with a vacuum chuck, okay, and they're looking at the copper side. They come along with a vacuum chuck and go, and they pull off the film. It's a freestanding thin film, just like this, okay. So that's how complicated it is. It costs next to nothing to do. It's a batch process, but you can do thousands of wafers in parallel. And so, and it's very low tech. It's just a container for acid. Okay, so that works. The cost is very low, and you end up with these films. And you can see it was right here, the same idea. And this property of thin semiconductors is that they are surprisingly bendable, and they work fine that way. Now, this was at a board meeting of Alta Devices. They had a customer that was putting the solar cells on an unmanned aerial vehicle. So here you have it. This is myself, and here you have Harry Atwater, and this is one of the venture capitalists here. And it shows, well, the fact that it's flexible changes a lot. The fact that it weighs next to nothing. Also, it's definitely the highest power to weight ratio and so forth. So this is all good stuff. Okay, now, but what has happened to the company? So the company ran into a problem. I'll describe the problem. But you have to know what's going on in the solar economy. There are a lot of solar panels being produced. I should mention that this is close to a $100 billion a year business. And it's dominated, 90% market share is silicon, crystalline silicon. Efficiency varies from 15% up to 23% efficiency. And the more technically savvy ones get up to close to this efficiency. However, what happened about 6-7 years ago in China is they got very excited about this. Every province in China wanted to be the world capital of solar panel manufacturing. And so they built up a huge amount of capacity. And they built up a capacity of 60 gigawatts a year, whereas the worldwide demand is only 30 gigawatts a year. So they overbuilt the capacity by 2. And I was joking at lunch today is that the central government in China got very worried about this, and they told the provinces, if your factory is less than a gigawatt a year, we're going to have to close you down. We have too many factories. And they very quickly, before the regulation went into effect, they very quickly built up capacity to a gigawatt. So now it was way over. It was over before. Now it's way over over capacity. As a result, there has been a price war. And the price has settled down to around 60 cents a watt. And it's kind of useful information because it tells you, which people never knew before, what is the true variable cost of manufacturing a silicon solar panel? Because people shut down a factory when it can no longer cover the variable cost. Forget about the fixed costs. You've written those off already. So that's all wasted investment by these provincial governments. But the variable costs, it's kind of interesting. So it means it really hasn't been that big an improvement technologically, because if you throw in the fixed costs, it's probably $1.20 a watt, which is roughly where we should be. And we'll eventually get down to 30 and 40 cents a watt, but not on the path we're on right now. But this price war has had an extremely bad effect on other companies in the business and on the new technologies. So all of the new technologies have been sort of shut down. There used to be great hope for copper, indium, gallium diselenide. That was the Solyndra company. I never understood Solyndra. I would drive back from my own company, which was closer to San Jose, and I saw the big Solyndra building. And then I drove back once, and they have another building even bigger than the original building. And I complained to the venture capital, that's crazy, we should be getting that money. They don't have any technology. And indeed, in the Bay Area alone, there were 20 copper, indium, gallium diselenide companies. Ridiculous. And none of them had anything. Solyndra had nothing. They had no technology. It was crazy. They're shut down. They're all shut down now. Now, there's a company, First Solar, produces cadmium telluride. Interesting technology. It's polycrystalline. Doesn't work that well, but it's good enough for them to be a player, and they might have about 5% of market share worldwide. Low quality polycrystalline cad telluride. The concentrators, you know, they're giving away flat plates for almost nothing. Who wants to pay money for concentrators? So the Chinese companies are in trouble. The American companies are in worse trouble. But there's something keeping the American companies alive. And what that is that the utilities were given mandates to install solar panels. I don't know if it was done in North Carolina, but in other states, they were given mandate. You must have 25% of your production must be from renewable sources. So what they did is they put in fixed price orders. This was about 2012. They put in fixed price orders for delivery, but when the mandates, by the time the mandates would take effect, which was 2018. So these companies have contracts to deliver panels at the old price, and the contracts extend until 2018. And these contracts are the only thing of value in the companies, because they might as well shut down, buy the panels from China, and the only thing of value that they have is these fixed price contracts. Okay. And that is what is keeping the industry alive today. Wall Street is perfectly happy with that. You can look them up. The bottom has been reached. These companies have a significant market cap on Wall Street, but it's somewhat artificial. It's being kept alive by these old fixed price contracts. What happened to my own company is that we sold it. We thought it was a great technology, and it is a great technology, but to take the next step, to scale to where the cost would really be low, and I should tell you what the costs are, because there's no big secret about this. So we projected a cost of 50 cents a watt at very high efficiency. We were getting about 80–90% yield of over 25% efficient cells. So our yield was fine, everything was fine. There's one little problem, that to scale up, the next step in the scale up was going to cost $200 million. And in this environment with a price war, none of the investors were willing to step forward and agree to buy the company, because if you buy the company, it means you'll have to spend another $200 million to make something out of it. Except one guy stepped forward. He's the third wealthiest billionaire in China. Chairman Li, we call him. And I've met him. And he bought the company, and he's a good businessman. He didn't overpay. I would say he underpaid. And he's putting new investment into the company, but not 200 million. He's scaling to a smaller scale to go after more specialized markets. But it's been very exciting. The technology will appear. You will be able to buy. You can buy these now for a price, but it's pretty good, and it's way more efficient. It has many other advantages compared to the normal solar panel. So I expect to see more of this in the future. So let me invite lots and lots of questions, and sociological, business, economics, anything you want. Okay, thank you for listening.